Previously, we talked about how electric charges can build up on surfaces and create something known as static electricity. In this episode, let's talk about what happens when these electric charges continuously move in a process known as current electricity. Most electronics, everything from your refrigerator to your smartphone, requires current electricity to operate. Let's assume that we have a copper wire that's filled with copper atoms. Copper is one of those elements that has only one electron in its outermost shell, which means that with only a little energy, that electron can be easily ejected. If we push a free electron into the copper wire, it will eventually find a new atom to latch onto. The negative charge of that electron will eject another electron from the outer shell, which will then move on to the next atom, and so on and so on. This chain of moving electrons creates a flow known as electric current. Some elements, like copper, aluminum, and gold, can move electrons easily and are known as conductors. We can look at moving charges in another way. Let's say that this tube is a conductive wire and the steel balls are negative electric charges, electrons in this case. We might think that one charged particle needs to move completely through the conductor to create a flow, but that's not actually the case. As we push a ball in one end, the force causes all the balls to move and one pops out the other end. As you can see, one electron, even if it doesn't move very far, can force all the other electrons to move, creating a flow. What we just showed was electric current, which is a flow of electric charge. In most circuits, this is accomplished by moving electrons. The unit for measuring current is the ampere, which is often abbreviated as amps and written with a capital A. 1 ampere is defined as 1 coulomb of charge moving past a point per second. Let's look at a cross-section of wire carrying an electric current. If it takes 3 seconds for 6 coulombs of charge to move through that cross-section, then we say that 2 amps are moving through that wire. Unfortunately, electric current doesn't just magically flow through wires. It needs a little help. If left alone, the electrons in a wire won't move. We need to give them a little push. To do that, we'll use a voltage source like a battery. In a battery, there is a buildup of negative charge on one side in the form of excess electrons. The other side has a buildup of positive charge, an absence of electrons in this case. The charges want to balance out, but the only way to do that is for the excess electrons to flow around the battery through a conductor that we provide. If we connect a piece of wire to the negative terminal, the electrons will push against the electrons in the wire. However, air is an insulator as its molecules do not have very mobile electrons, and it won't readily accept the free electrons. To show this, we'll put a piece of tape at the end of the tube. Now, the electrons at the end of the wire have nowhere to go. Even if we push against the electrons in the wire, they still won't budge. To fix this, we need to connect the other end of the wire to a place where the electrons want to go, and the positive end of the battery will happily accept the electrons. In fact, don't try this with a real battery. There is nothing slowing down or restricting the flow of electrons, which results in tremendous amounts of energy being transformed into heat in the wire, and this could easily melt the wire insulation or start a fire. This is known as a closed circuit, as it creates a loop from one side of the energy source to the other. If we break the wire or remove it from one of the terminals, then the electrons will stop flowing. This is known as an open circuit. We've been talking about electron flow in a circuit and showing how electrons move from the negative terminal to the positive terminal. However, in electronics, we usually assign current as flowing from positive to negative, or from higher potential to lower potential. This is known as conventional current. In the mid-1700s, Benjamin Franklin theorized that positively charged objects had an excess of what he called electric fluid, and that negatively charged objects had a deficit of this fluid. Franklin noted that this fluid had a tendency to flow from positive to negative to distribute itself more evenly. It wasn't until the end of the 19th century that English physicist J.J. Thomson discovered the existence of the electron. Even though we now know that it is electrons that move inside of most circuits from low to high potential, the convention of current moving from high to low potential stuck. As a result, most current measurements are given as conventional current, which is the movement of positive charge in a circuit, and is represented by the capital letter I. Don't worry, the math still works out as long as we stick with either electron flow or conventional current. And since most electronics textbooks use conventional current, we'll go with that. We talked about making electricity do work for us, and the circuit forms the basis for all modern electronics, everything from the simple flashlight to massive supercomputers. If we made a circuit out of just a battery and a piece of wire, there's a chance we might melt that wire as the electrons move through that wire at an alarming rate and generate massive amounts of heat. In the next episode, we'll talk about the relationship between voltage and current and introduce the resistor.
Let's get stuck into parallel and series circuits. Irresistible. First, you need to know these 12 circuit symbols. You've got 5 seconds. But you do them anyway, right? Right. Circuits come in 2 variations, series and parallel. But what's the difference? In a series circuit, there is only one possible route for current to get from one side of the cell to another. In a parallel circuit, it can take more than one route. It can go through this bulb, or through this one. What the heck? Why not do both? Current is flow of moving charge. The more charge flows, the higher the current. In a series circuit, the current flows through each component in turn, and there are no alternative routes. Each part of the series circuit has the same current, measured in amps. Nice moped! In a parallel circuit, the current has to divide itself between the different paths. These 2 bulbs are identical. So in the parallel part of this circuit, the current is split in half, and each bulb gets just 0.1 amps. Okay, but why does current flow? Why bother setting out from that cosy little cell in the first place? The electric charge wants to get from one end of the cell to the other. For electrons, this is like going downhill. They love it. But they can't go through the cell, not allowed. So they have to go round the circuit. The difference between the ends of the cell is called the potential difference, and it's measured in volts. For the standard cell, this is 1.5 volts. In a series circuit, the potential difference is shared. So these 2 identical lamps share the 1.5 volts from the cell, half each. But in this parallel circuit, both bulbs have the full potential difference across them. So opposite things happen in series and parallel circuits. This being science, we'll measure stuff, namely the current using an ammeter and the potential difference using a voltmeter. First, current. How do we measure the current flowing through this bulb? The ammeter will tell us the size of the current measured in amps. It needs to go into the circuit in series to measure the full current. Yep, round about there. And to measure the potential difference across the bulb, the voltmeter has to be connected in parallel. That way, we measure the same potential difference as is across the bulb. Positioning is everything. The usual type of cell supplies 1.5 volts. If we put 2 together in series, then the potential difference is doubled to 3 volts. That's enough to power some pretty cool stuff. If we join them the wrong way, it's not going to work. The potential difference of one cell is cancelled out by the other. No current flows. If we add more batteries, we increase the potential difference across a component. We're also increasing the current. Eventually, the component will break. Shame.
This is not a battery. I know it looks like a battery, but it is not a battery. At least, not in the science sense of the word. Now, this is one of the things that I wish I could change. I mean, if I was in charge of the world, I would change many, many things. And the way that we use words in everyday, and then the way that we use words in science, it would be one of the things that I would change. Because they don't necessarily match up. And when you're trying to learn stuff for your GCSE, the fact that words you've been using ever since you could speak now means something completely different is sometimes really, really hard for you to get your head around. So this is a cell, okay? If I had 2 or 3 cells in a row, then they would make a battery. Now, if we think about our flashcards, our circuit symbols for physics, see, here is one cell, that is it, on its own, and then if we want to have more than 1 cells together, yeah, that makes sense. There we go, can we see that? That is a battery. Cell, one on its own. Battery, lots of cells together. So it is a common misconception. It's one of the things that confuses people a lot in physics and in chemistry, the difference between a cell and a battery, which is lots of cells put together. Okay? If I could change it for you, I would, but I can't. so I'm sorry.
Hi guys, this is I'm Stuck, and today we're looking at electrical circuits and their symbols and the functions of these components. So first of all, we're going to look at a cell. Now a cell is in nearly every single circuit and it pushes the electrons around a complete circuit. Now a battery is also contains of 2 or more cells, and that's again, a battery is used in a torch, for example. You would have a cell. Then another very important one, especially when you think of turning a light on, is the switch. Now this enables the current in a circuit to be turned on or off. And as you can see, the pictures are going up on your screen. Then a diode allows current through one direction only, which means it is only direct current because it's only going one direction, it can't alternate, and we'll talk about that in another video. A light emitting diode, which is also known as an LED, and that emits light when a current passes through it. So when the current passes through it, it acts like a light bulb and it emits light. Then an ammeter is used to measure electrical current. So this is constant use, and this is in series is constantly in series in the circuit, and we'll talk about in series and in parallel in another video. Then a resistor, and that limits the amount of current in a circuit, and that's the one without an arrow through, and the one with an arrow through is a variable resistor, and that allows the current to be varied. Then there is a fuse, and this melts if the current in a circuit gets too hot, and again this will be another one that I'll go into more detail in another video because it's quite important, fuses and circuit breakers. Then finally, a voltmeter measures the potential difference, and that's the potential difference is the voltage, and this is always connected in parallel, and again I will talk all about that in another video. So make sure, if you want to know all the symbols, make sure you look back through this video and look through the symbols, because you have to know all the symbols and also their functions so you can design your own electrical circuit, and in an exam, if they ask you for these symbols or the functions, you will know them. So thank you very much for watching this video. Can you please watch other videos which will be coming up about series and parallel circuits, and we'll do a bit about circuits at the moment on this channel as well as all the other videos. But for now, can you visit my website and please subscribe to my channel. See you soon. Bye.